Hey everybody, in this video I'll introduce and explain a commonly used gas law known as the ideal gas law. So remember that most recently we've seen the combined gas law that has pressure, volume, and temperature. And it's called the combined gas law, of course, because it's made up of Boyle's law on top with just pressure and volume, and Charles' law over on the right with just volume and temperature. Now what's extra important about all three of these gas laws is that they all describe a gas that's undergoing a change. That's the reason we have these subscripts of 1 and 2, right? These are your initial conditions and your final conditions. In this video, we'll introduce a new gas law that will show you not all gas laws have to work this way. The gas law we're talking about is called the ideal gas law. This is not about a gas undergoing some sort of a change. It is a mathematical model that lets us predict pressures, volumes, and temperatures, except now we're going to also factor in the amount of gas particles. That means how many gas particles are there. You might also notice that it specifies that these gas particles are ideal. This video isn't going to cover exactly what that means, but rest assured that we can apply this gas law as a good approximation for most gases. So here's the mathematical equation associated with the ideal gas law. P times V equals N times R times T. Now right away you should recognize P pressure, V volume, and T temperature. But we've also got some new variables in there, the N and the R. You might also notice that there aren't any subscript 1s and 2s. That's because, again, this gas law does not describe a gas undergoing a change from an initial scenario to a final scenario. The lowercase n in the equation is what we mentioned earlier. That is the amount of gas particles that are present in the sample. And just like we always do in chemistry, when we're counting the amount of particles, we do it in moles. So your lowercase n is the amount of moles of gas particles that your sample contains. And the capital R is something called a gas constant. The best thing about constants in equations are that they're just numbers. You just plug them in. Now the only challenge we have with capital R, the gas constant, is that there's lots of them. Here's one value that you can use, 0.08205. Here's a second one. There's actually lots of different versions. For this video, we'll just focus on these two. So why would there have to be multiple different R values? It's actually there to make life easy on us. We can plug in and use whichever one of these things we want. So let's imagine I wanted to use that first one, 0.08205. If I use this R value, that's totally fine. I just have to make sure that all of the other numbers that I plug in, so that means the P, the V, the N, and the T, their units have to match all of the units associated with that R value. So let's walk through some of these. The first unit there I see is liters. That means the volume that I plug in now has to be in liters. Then I see ATMs, that's a pressure, so the P that I plug in has to be in ATMs. The temperature, of course, has to be K in Kelvin, and of course N is just moles, and we see moles down there in the units of R, reminding us to plug in moles for the lowercase n. If you wanted to use the other R value, 8.314, that's also completely okay as long as you make the units match that one. Now you might notice most of them are the same, liters, moles, and Kelvin. The only thing that's even different is the pressure, kPa. So if I want to use 8.314, then I wouldn't plug in ATMs, I'm going to plug in kPa instead. That equation and those R values are your key ideas for this video. Make sure you pause and take a minute to write them down. That wraps it up for this video. Make sure to check out the next in the series where we'll look at some example problems applying the ideal gas law. Here's a brief summary.